Okay, following with question C, it asks you to sketch the graph if the substrate had initially been 1.5 times 10 to the negative 6 molar. So if one thing to consider is that if you change the concentration of the substrate, you would expect the velocity to be changed as well, right? Because we say that the velocity of the reaction would depend on the concentration of the substrate. And to calculate the velocity of the reaction, you would need to know the kinetics of this enzyme. So first, we know that this enzyme T has a Km equal 1 times 10 to the negative 6 molar, but the questions doesn't give you the value of Vmax. So you need to come up with the value of Vmax first in order to use the Km and Vmax, and then use the Michaelis-Menten equation to solve for the velocity of the reaction. So in this case, you can find the Vmax of this enzyme T by through different methods. So the first one, to calculate the Vmax, you can also use the Michaelis-Menten equations to solve for Vmax. So you know that V naught equal to Vmax times by the concentration of the substrate, and then divide by Km plus the concentration of substrate. So from the equations, we know that V naught, our V naught here in this case from equation A equal 0.5 nanomole per second. And then we want to solve for Vmax, and then you plug in the concentration of the substrate here, which is equal 30 millimolar. And then divide by Km plus the concentration of substrate. So I would change the concentration of substrate in the unit of molar in order to be easy to calculate. So 30 times by 10 to the negative 3 molar. 30, 10 to the negative 3 molar. So you can find the Vmax from this equation and solve for Vmax. So the alternative method is that one thing to notice from this question is that initially the concentration of the substrate is equal 30 millimolar, and then the Km is 1 times 10 to the negative 6 molar. So if you run the assay and the concentration of the substrate is higher, is greater than the value of Km more than 100 times, so we assume that that velocity from that reaction would be equal to Vmax, correct? So you if you have the graphs of we plot against the concentration of the substrate, you would have something that look like hyperbola, correct? So the maximum of this velocity is equal to Vmax, and the point of half Vmax will give you the value of the Km. So from this graph, we learned that if the concentration of the substrate is like greater beyond the Km many times, for example, like this. So at this point, the velocity would reach Vmax. So that's why we can, from the question that we were asked, we can assume that if you run the reaction with the concentration of substrate is greater than the Km, the velocity, the initial velocity that you got from that reaction is actually Vmax of that enzyme. Okay, going back to our questions here, as now we can assume that initial velocity is equal to Vmax. So that means our 0.5 nanomole per second here is actually Vmax. So we can use this Vmax value and then the Km value from here and calculate for the new velocity of the new concentration of the substrate. So plug in Vmax and Km in the new Michaelis-Menten equation and you will get V naught equal 0.3 nanomole per second. This is the new velocity with when you run with the new concentration of the substrate. But the questions ask you to sketch the graph. So I'm gonna put this new velocity into the graph above. So note that since we got 0.3 nanomole per second and we want to plot it into the same graphs, so it needs to corresponding to the initial graph here. So if, and I want to plot in like 50 seconds also. So you can calculate that in 50 seconds, what would be the velocity? So it would mean V0 would mean 0.3 times by 50. And this would be equal 15 nanomole in 50 seconds, correct? So I want to plot this velocity in the graph here. So if we begin at the baseline, which is 5 here, so 5 plus 15 would be 20. So you know that the velocity at the times of 50 seconds would be 20. So you can plot a new graph to reach that point. So this red line over here is the new V naught here. Some people might ask that why we need to plot the graph starting at 5. So the reason for this case is that because, I mean, when you assay with the enzyme reaction at time 0, maybe you might capture some signal that is like a baseline. So it might be something that have like absorbent, but we know that that should be our baseline, right? So we need to take that into account of why we're starting at 5. But if, I mean, you can also plot the graph starting at 0, that's fine too, as long as this new graph here has the slope equal to 0.3 nanomole per second. Yeah, that's absolutely acceptable. So for the last part here, it's asked you to calculate the turnover number of the enzyme. If 1 times 10 to the negative 12 mole of enzyme T were present. So to calculate the turnover number, so turnover number of the enzyme actually means like how frequently the enzyme T got used in the assay. So for here, you notice that the amount of enzyme that we have here is just 10 to the negative 12 mole, whereas this amount of enzyme need to convert at about have to convert the substrate at about 0.5 nanomole per second. So I mean per second is it need to convert substrate like 0.5 nanomoles, and 10 to the negative 12 is also less than 0.5 nanomole. So you would imagine that your enzyme need to like work multiple times in order to conduct the conversion of the substrate at that rate of Vmax. From the lecture, the turnover number is K2 turnover number. So the equation that from the lecture is that K2 equal to Vmax. So every turnover number need to be calculated under Vmax conditions. Vmax divided by the total amount of the enzyme. And this should be in the unit of mole. So you can plug in the number here. Vmax is 0.5 nanomole per second. And then divide by the total amount of the enzyme, which is 10 to the negative 12 mole here. So I will change Vmax in the unit of mole. So it's actually 0.5 times 10 to the negative 9 mole per second, right? So your turnover number would equal 500 per second. So it means that your enzyme need to work 500 times in 1 second to convert under the condition of Vmax. So if you want to calculate the turnover number per minute, you can also time by 60 to convert into the minute. So it would also equal 500 times by 60. So you get 30,000 times per minute. Okay,